Mio Kaku once remarked that we will need to revise our textbooks on the origin of the universe. People have been eagerly awaiting a particular image, and that image has now been released. This image from the James Webb Telescope reveals extraordinary phenomena in the universe that challenge our scientific understanding. Since the telescope's launch, not only have our theories about the beginnings of the universe been tested, but even exoplanets are defying our understanding of physics, completely reshaping our ideas. What new possibilities and answers will scientists discover as a result of these revelations? We are witnessing a total disruption of the old scientific principles. The James Webb Telescope is revolutionizing our perception of the universe, and each new image from this marvel of space exploration is groundbreaking. The telescope is named after James Webb, who was not a scientist but came from a business background. Webb understood the importance of space exploration for humanity, having led NASA during the 1960s. Under his leadership, space travel advanced significantly with the launch of the Apollo program and a push for space exploration. Today, scientists are in awe of the telescope's capabilities. The images it provides are so sharp and detailed they take our breath away. For the first time, we are getting detailed studies of exoplanets located millions of light-years away. The telescope is revealing that the scientific community has been relying on outdated concepts for far too long. At first, many scientists are feeling uncertain and uneasy as everything they once believed is being called into question. One expert who is optimistic about these developments is renowned astrophysicist Michio Kaku. Kaku has long argued that our previous theories were incomplete. The inability to reconcile the subatomic world with the world of matter alone shows we have not fully understood the fundamental processes in the universe. Now, exoplanets are also defying the laws of physics, which is astonishing. Initially, only ancient worlds didn't fit into our cosmological models. Then came black holes and massive structures older than 13 billion years, from a time when the universe was still in its infancy. Now, even planets are defying our previous understanding. The latest images from the James Webb Telescope show exoplanets that challenge our former notions of planetary science. The telescope's sharp eye and powerful spectrometers allow it to separate even the faintest light signals into their components, revealing traces of elements, gases, signs of water, and data that indicate the size and orbits of distant planets. Webb is uncovering so many anomalies and limits that it's almost impossible to categorize these findings. One example is K2-9b, an ultra-hot Neptune orbiting so close to its star that its surface temperatures are high enough to break water molecules into hydrogen atoms. The planet's proximity to its star causes a phenomenon called atmospheric blow-off, where the planet's atmosphere is literally blown away. This discovery is extraordinary and presents a significant challenge to our understanding of planetary climates. Another fascinating planet is WASP-76b, a giant exoplanet where iron rains down from the sky on its night side. The planet orbits its star in a tidally locked orbit, resulting in extremely hot and cold sides. On the hot side, metals melt and evaporate, while on the far side, the metals cool and solidify, eventually falling as rain. Scientists are dealing with extreme conditions that push the boundaries of our understanding of planetary processes and raise more questions than answers. Equally intriguing is the discovery of planets that orbit their stars in the opposite direction of other planets in the same system. Such findings force astronomers to rethink theories about the dynamics of planetary systems and the forces that determine their orbits. WASP-7b is an example of such a planet, a gas giant similar to Jupiter, but one that orbits its star in a retrograde orbit, opposite to the star's spin. This was once thought to be impossible according to current theories of planetary formation, which suggest all planets in a system should orbit in the same direction they formed from the original protoplanetary disk. One explanation for such retrograde orbits is that gravitational disturbances from nearby stars or other large planets can significantly alter a planet's orbit after its formation. We don't even need to look beyond our own solar system to find strange planets. In the Kuiper Belt, there's the dwarf planet 2018 VG18, which has proven to be unusually dark and red. Webb spectrometers reveal that it is likely rich in complex organic compounds known as tholins. Despite its significant size, 2018 VG18 has not yet been officially named, and its exact orbit has yet to be determined. Its unusual composition, rich in organic molecules that are the building blocks of life, sets it apart from other dwarf planets in the Kuiper belt. This raises questions. Where did this planet come from? How did it form? And why is it so difficult to observe, given its elongated orbit? One of the most mysterious types of planets discovered is the rogue planet. These planets, which do not orbit a star, float freely through space. It was once thought that planets always form in the gas and dust disks around stars, remaining gravitationally bound to their star. However, rogue planets challenge this assumption. They can form in various ways, such as being ejected from their original star systems due to gravitational interactions with other planets or passing stars. Another possibility is that rogue planets form in isolation, without any star, and float freely through the vast emptiness of space. How do these planets survive in the hostile cold of space? And what secrets might they hold? The discoveries made by the James Webb Telescope are truly rewriting the rules of astrophysics, forcing scientists to reconsider long-held beliefs about planetary formation, the dynamics of our solar system, and the very nature of the universe itself. Each new image and finding pushes the boundaries of what we thought we knew, providing a deeper and more complex understanding of the cosmos. The cooperative approach of combining data from multiple ground-based and space-based telescopes, known as multi-frequency stargazing, enhances our understanding of complex astrophysical processes and astronomical events. By integrating information across various light frequencies, researchers can develop comprehensive models of celestial objects, from distant galaxies and black holes to the dynamics of galaxy clusters and the cosmic web. Operating the James Webb Space Telescope, JWST, presents significant challenges. Its sophisticated instruments must function at extremely cold temperatures, close to absolute zero, to minimize interference from their own heat radiation. Additionally, the telescope's large, delicate sun shield, roughly the size of a tennis court, protects it from solar radiation and helps maintain its thermal stability. These engineering feats are the result of meticulous planning and years of collaborative work between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Despite these challenges, the JWST has already begun to deliver remarkable scientific results. Communication between Earth and the spacecraft takes approximately 2 days, which makes it difficult to implement timely solutions or make iterative adjustments, a common necessity when addressing complex technical issues. The engineering team must carefully plan and execute each command, accounting for various scenarios and possible outcomes. Unlike missions closer to Earth, where engineers can send and receive instructions quickly, the significant communication delay demands a more strategic, patient approach. Every command must be precise and thoroughly tested on Earth before being sent to the spacecraft, as there is little room for error. Moreover, the spacecraft itself is over 40 years old, having been launched in 1977. While its technology was state-of-the-art at the time, it is now considered outdated by modern standards. Engineers are working with systems designed in the 1970s, adding another layer of complexity to the troubleshooting process. The harsh environment of space, with cosmic radiation, extreme temperatures, and micrometeoroids, has taken a toll on the spacecraft systems over the years. These factors contribute to the wear and degradation of its components, making maintenance and repair even more challenging. Despite these obstacles, the engineering team is committed to addressing the issues and exploring potential solutions through simulations on Earth. They are investigating various theories about the cause of the anomalies and testing possible fixes. Given the high stakes involved, any incorrect command could exacerbate the problem or cause a loss of communication with the spacecraft. The team is also leveraging the redundancy built into the spacecraft systems, as many space missions, including Explorer 1, were designed with backup systems to increase resilience to failures. If a part fails, engineers may be able to switch to these backup systems and restore normal operations. In summary, while the challenges of diagnosing and fixing issues with Explorer 1 are immense, the engineering team is using their expertise and the spacecraft's inherent durability to tackle the problems. Their careful and patient approach is essential in managing the significant communication delays and the complexities of operating a spacecraft that is both incredibly distant and aging. Despite the odds, their efforts are ensuring that Explorer 1 continues to contribute to scientific exploration and discovery, far beyond its original mission parameters. The glitches may be due to cosmic rays interacting with the spacecraft's sensitive electrical systems. These high-energy particles, originating from supernovae or other cosmic events, travel through space at nearly the speed of light. When they strike Explorer 1, they can penetrate its outer shell and affect its internal electronics. The longer the spacecraft stays in space, the greater the likelihood that cosmic rays will impact its systems, which can lead to irregularities in the telemetry data. Engineers have long been aware of the potential risks posed by cosmic rays to spacecraft hardware and human travelers, but predicting and mitigating their effects can be difficult. Even with protective measures like shielding sensitive equipment, redundant systems, and error-correcting codes for data transmission, cosmic rays can still pose a threat, especially to spacecraft operating in deep space for extended periods, as in the case of Explorer 1. While the recent anomalies in Explorer 1's data are concerning, they are not entirely unexpected given the spacecraft's age and prolonged exposure to cosmic radiation. Engineers and scientists continue to monitor the situation, analyzing the data received from Explorer 1 and working to identify the precise cause of the anomalies. They are also developing strategies to minimize the impact of these cosmic rays on the spacecraft's operations. Despite these difficulties, Explorer 1 has far exceeded its original mission expectations and continues to provide valuable insights into the outer regions of our solar system and beyond. Its achievements are a testament to the ingenuity of its creators and the dedication of the team that has supported it for more than 4 decades. The journey of Explorer 1 symbolizes humanity's relentless curiosity and determination to explore the uncharted expanses of space. And future missions like Explorer 1 will continue to push the boundaries of our understanding of the universe. In regions where stars form, there are objects with insufficient mass to initiate nuclear fusion processes like stars. These objects, often referred to as jumbos, are similar to Jupiter in mass but lack the necessary mass to trigger fusion and become stars. Jupiter, the largest planet in our solar system, is just short of the mass required for these processes. The James Webb Space Telescope, JWST, shocked the scientific community when it discovered 80 such Jupiter-mass objects in the Orion Nebula. What makes this discovery even more intriguing is that these 80 objects are part of 40 binary systems, meaning 40 pairs of these drifting planets orbit each other within the confined space of the Orion cloud. This is odd and scientifically puzzling. The sheer number of these objects could be linked to the fact that the Orion cloud is one of the most intense star-forming regions known. However, further research revealed that these objects are not true planets but rather substellar objects with masses between planets and brown dwarfs. This suggests they are failed stars, as brown dwarfs are some of the smallest stars known. The question arises: what processes in the Orion cloud lead to the formation of these objects, which behave like planets but move freely through space in binary systems? This discovery challenges existing astronomical models and could indicate that such massive free-floating objects are more common in the universe than we previously thought, but are rare to us because we were unaware of their existence. The JWST marks a significant breakthrough in our ability to detect exoplanets and study their environments in detail, addressing one of the biggest challenges in space exploration: identifying and studying distant exoplanets. Unlike its predecessor, the Hubble Space Telescope, which primarily observed visible and ultraviolet light, the JWST is designed to observe in infrared wavelengths. This allows it to peer through cosmic dust clouds, study star and galaxy formation, and even analyze the atmospheres of far-off exoplanets. One of its main goals is to unlock the mysteries surrounding the early universe, such as understanding the formation of the first stars and galaxies and how they influenced the evolution of the cosmos. In addition to studying distant galaxies, JWST is revolutionizing our understanding of exoplanets, planets that orbit stars outside our solar system. The telescope's advanced instruments can directly image these exoplanets and study their atmospheres in unprecedented detail. By detecting chemical signatures in the atmospheres of these planets, scientists can learn about their temperature, structure, and even their potential for habitability. The discovery of exoplanets has been one of the most exciting advances in astronomy in recent years. Before the launch of JWST, Astronomers primarily relied on indirect methods like the transit method, measuring the slight dimming of a star as a planet passes in front of it, and the radial velocity method, detecting wobbles in a star's motion due to the gravitational pull of an orbiting planet to detect exoplanets. While successful, these methods provided limited information about a planet's size, mass, and orbit. JWST promises to transform exoplanet research by directly imaging these distant worlds and analyzing their atmospheres. This capability is crucial for identifying potentially habitable exoplanets, worlds where conditions may allow for liquid water and possibly life as we know it. Understanding the diversity of exoplanetary systems and their atmospheres will provide valuable insights into the prevalence of life in the universe. Beyond exoplanets and early galaxies, JWST's suite of instruments includes cameras, spectrometers, and coronagraphs, each designed to capture different aspects of the universe. For example, the near-infrared camera (NIRCam) enables high-resolution imaging across multiple infrared wavelengths, while the near-infrared spectrograph (NIRSpec) analyzes the light from distant objects to reveal their chemical compositions and physical properties. One groundbreaking feature of the JWST is its ability to perform structured observations across a wide range of cosmic phenomena. In summary, the James Webb Space Telescope is not only revealing the unexpected and previously unknown, but it is also rewriting the book on how we study the universe, challenging old assumptions and pushing the boundaries of modern astronomy.